Okay, so good morning, everyone. So let us continue from what we were discussing yesterday. So we have discussed several operations on processes, which mean how to create a process, how to end a process like exit, or how can a parent fork another process, which is a child. How can the parent wait for the process and so on. Now what we have started discussing is how processes can communicate. And we have discussed that processes may need to communicate due to many different reasons, as written in this slide. They may actually need to cooperate in doing a large task faster, or the condition may be such that one process can do its job only after the other process has done something. Right, so all these things or all these situations make it necessary for processes to communicate. Now, the kernel understands that processes may need to communicate, and therefore it gives several types of IPC support. IPC is inter-process communication. So let us see some of these IPC supports provided by a standard Unix or Linux system. So here are 4 ways of doing IPC: shared memory, message passing, which has again 2 variants. One is called a pipe, another is called a named pipe, and finally over network. So as I said, this 4th way of doing inter-process communication over a network, that means 2 processes running on 2 different machines. This we won't cover in this course. This is what you will learn in the networks course. So we will see the first 3 now. So as you can see, there are several system calls associated with each of these IPC mechanisms. I'll introduce you to some of them, but yeah, we won't go into too much details about any of these. You are expected to read the man page or read some other material or a book to understand the more details about these system calls. But we will introduce you to those system calls and kind of understand how they are used. Okay, so let us start discussing a shared memory system. So the idea is this, as shown in this picture. Process A and B needs to communicate. So they take the help of the kernel to create a common segment in memory. So this is this is a common segment which both A and B can access. Understand that this is different from what we discussed earlier. Like process A has its own data segment, stack, etc., which B cannot access. Similarly, B has its own data segment, stack, etc., which A cannot access. But this is a different area of the memory which both A and B can access, and that is why they require the help of the kernel to establish such a shared memory. Now there are several system calls which are needed to create and then operate such a shared memory, like SHM get, SHM at, etc. As you see, all these system calls start with SHM, which is shared memory, right? So shared memory get, at is for attach, DT is for detach, etc. So let us see these system calls. So here is some code. Let me explain the codes. First of all, see, we define some kind of a key, some unique ID, the 235. This is, you might say, the key associated with the shared memory. So of course, both the parent and the child should use the same key. Next is this line, this SHM get. This is the line which creates the shared memory segment. So you see, SHM get takes as arguments the key, then some other value. We are not focusing on this right now, but this we are focusing on. First of all, let's see this 0666. Does this remind you of something? Maybe something we briefly discussed a couple of weeks back. The 0666. First of all, what does the 0 tell you? This is nothing to do with operating system. This is from C programming knowledge. Something that you have learned in PDS, I guess. What is the 0 doing here? Why not just 666? Exactly what Dhrumil said. This is an octal number. So 0 signifies it's octal. Yeah, and what is the 0666? Yeah, Shubham has answered. correctly, these are the permissions. So if you remember, we discussed that a couple of weeks back that yeah, so the 0 means octal and 666 is the permissions. If you remember a couple of weeks back, I showed you the output of an LS and said, and we discussed that every folder, every directory has some permissions as to which users can access that file or directory. So, and there were 3 types of permissions: read, write, execute. Similarly, there are 3 types of users identified. One is the owner of the file or folder, okay. Another is the group of the owner. The other set is others. So owner, group, others. So these 3 numbers tell what are the permissions are for owner, the first number, for group, the second number, and others, the third number. And what about 666? What does this say? Like, these are permissions. No, so how does the number 6 come? What should I understand by 6? Exactly, what Somnath has pointed out. Good. So, no, sorry. No, Somnath has given the correct idea, but the values are not correct. Shubham is indicating the right answer. So as I said, there are 3 types of permissions: read, write, execute. Read is considered, or read is given, again, these are octal numbers. So read is given a number 4, right, like 100. Write is given the number 2, 010, and execute is given the number 1, 001. Right, so 6 means 4 plus 2, read plus write. So here it seems all the users have read and write permission. But this permission is not associated with any file. This is associated with the shared memory segment which is getting created. Okay, so this shared memory segment is getting created by this call, and it is said to give a permission of 666. Okay. And again, this IPC create is a flag. I leave it to you to figure out what this is. It might be quite evident from the name, but yeah, I'm not telling you all details of this call. I'm leaving some part for you to figure out. And what does SHM get return? It returns an ID. It is the ID of the shared memory. Henceforth, all operations will be using this ID. Okay. Now, the next system call is SHM at. This is shared memory attach. So this system call is used to attach the memory segment to the address space of this process. Right, so the address space of this process till now was its address space. Right, so if I go back a couple of slides, the address space of process A was this only. Now A is requesting the kernel to attach the shared memory to its process also. Same thing would be done by B also. Okay. How is that done? This SHM at, then the ID of the shared memory which is created, and then again these I am not explaining. These I leave to you to figure out. So the exact details of the arguments, etc., I'm leaving it to figure out. And again, SHM-AT returns MySeg. What is MySeg? A char pointer. Right. So once this is done, you can just treat this as like another array or something like that. You can write to this memory segment, the shared memory segment. The other process which also shares this will be able to read it, and so on. Now you have a character pointer. So whatever you can do with a character pointer, you can now do with this shared memory. Now you do whatever you want to do with the shared memory. You write to it, you read from it, etc., etc. After you are done, you detach the memory segment from the address space of this process. Right. So for that is SHM-DT, is a shared memory detach. The shared memory attach was for attaching the shared memory to the address space of this process, and this is for detaching. Right. Finally is this call, SHMCTL. This is so shared memory control. This can be used for some other purposes also. Here we are specifically, the example here is marking the segment to be destroyed. So again, IPC RMID. Figured this out exactly what it means, but this basically means asking to delete this shared memory. Right? So okay, let me ask, why do you think both are necessary? Why is this detachment necessary and again this necessary? Of course, if you have any questions, then ask. Otherwise, I have this question. Why do you think two steps are necessary? Detachment and then mark the segment to be destroyed. Okay, so Pankaj, Somnath, Shrihash, you have all given answers in the right direction. So sure, finally the shared memory has to be deleted. Right? Otherwise, it will just occupy some part of the memory and we cannot afford that. Memory is precious. So of course it has to be deleted. But then see, just this call could have been given, just delete it. Why did the kernel give another system call called SHMDT? Why do you think? So of course it has to be deleted, but then SHMCTL would be enough, right? Why should there be a separate call called shared memory detach? Exactly. Pankaj has the right answer. Pankaj, Srihash, they have given the answer that I was looking for now. Or even, yeah, Pankaj, Srihash. So see, this slide is showing you just some code snippets. But think about how actually you would write the code when using shared memory. You will have at least two processes, maybe even more. So maybe 5 processes are sharing as a particular memory segment. Now, one of those processes work is done, but the other 4 would still like to use that shared memory. So this process can simply detach itself and, complete. This process whose work is done. Finally, so this call will be used by all processes which had once attached this memory to itself. But this call will possibly only be used by that process which had created the memory in the first place to finally remove it. Okay, that is why 2 different calls are needed. So I hope you get the idea that every process which once had attached this memory to itself should use the detach, but this final removal should be done only by that process which created it after it has ensured that no other process needs this memory. Okay, that is why 2 different calls are given. Okay. So any questions about shared memories before we go to the next? Next is an application of a shared memory. So before that, any questions? Okay, let me proceed. So let us discuss quickly on a small example of a small example where shared memory would be used. This is quite a famous example called producer-consumer problem. Actually, this is a kind of a notion which operating systems often use. If your networks actually, if you, as you are going ahead with the networks course, you will see this idea of a producer-consumer problem coming in there also. So this is just an abstract idea. We will discuss a couple of implementations, but there are many other implementations possible, maybe much more efficient than what we are going to discuss here. So the idea is simple. A producer, there are 2 processes, a producer and a consumer. The producer produces information and the consumer consumes it. Here are some examples, like the compiler produces assembly code which is consumed by the assembler. Or program produces lines to print, and the print spool, which is, let's say, a process which is handling the printer or controlling the printer, that is consuming it, right? And so on. So this is an abstract idea which has its application in many concrete problems. And there are 2 variants of this producer-consumer problem. One is called bounded buffer, the other is called unbounded buffer. What is buffer? Buffer is this place, this say hypothetical place or logical space where the producer produces items and from where the consumer consumes it. So the question is this buffer bounded or unbounded? Bounded means limited. So you see, if the difference is that if the buffer is limited or bounded, then at some point it can happen that the producer has produced a lot of items, the consumer has not yet consumed them. So there is a concept of a bounded buffer getting full, and then the producer should detect it is full and it should wait. Whereas the consumer can also have to wait if the buffer is empty. So maybe the producer has not produced anything, so then the consumer has to wait until something is produced. This is a bounded buffer where both producer and consumer may have to wait. In an unbounded buffer, the consumer waits only when the buffer is empty. There is no question of the producer waiting because the buffer is unbounded. That is a very imaginary scenario. Usually computer, computer memories, etc., they can be very large, but still they have some bound. But yeah, so there are these two variants of this problem. Quick question here. Have you studied anything in networks till now which reminds you of something similar to this? Okay, maybe not, fine, but you will soon see. So you will, yes, packets are pushed in a queue in a router. Yeah, that's one example, sure. But okay, even if it is not done in the network course now, you will soon come across it. Like there will be some mechanisms discussed about congestion control and things like that. So there also in networks also there is a producer process running in one machine and a consumer process running in some other machine. So somehow the producer has to take care that the consumer is not overburdened, as in it should not happen that the consumer is reading data at a much slower pace and the producer is going on pushing data at a very fast pace. Then all the buffers will overflow. So there are several mechanisms to prevent those things. This is the thing, that the producer has to wait when the buffer is full. Right. So of course in a network the situation is much more complex because the producer and the consumer is running on two different machines. So how does the producer even know that the consumer's buffer is full? So I'm sure that part will be discussed in detail in the networks course. There is a whole family of algorithms there called congestion control. So that would be discussed in the networks course. But here we are dealing with a simplified scenario where both producer and consumer are in the same computer, and therefore they can use shared memory to implement this buffer and to figure out when the buffer is full, etc. But whatever be the implementation, so this is the general producer consumer problem. So now see some implementation details, as in what can be a nice way of implementing this producer consumer paradigm using shared memory. So suppose you define a small buffer size, okay, 10, and then you define this structure. So every item of this buffer or every element of this buffer will be this structured item. Okay. So this is the shared memory. This is the shared memory. And we define two other variables in and out. Now these variables reside in shared memory. So both the producer and the consumer will have access to these variables. And of course this is just an array buffer. This is a linear array. We all know that arrays are linear. But as you will see in the next slide, conceptually this array will work like a circular buffer. Right. Conceptually this array will work like a circular buffer. I guess you all have written codes similar to circular queues and all. So I guess you get the idea. Like though I think physically it's a linear array, but logically we can make it behave like a circular buffer. So there are these two positions, in and out. In is the right position where the producer will put the next item. and out is the read position from where the reader will read the next item. Okay. So yeah, right is the in is the right position where the producer will write the next item, and out is the read position from where the reader will read the next item. Okay. So yeah, so in is the next free position to write to, and out is the next filled position to read from. So how to figure out if the buffer is full or empty? If in equal to out, then buffer is empty. So the consumer should check this, and if this is true, then it should wait. Similarly, what is the condition for buffer being full? In plus 1 modulo buffer size equal to out. This is the condition for the buffer being full. There is a small caveat here that this scheme which we are discussing allows at most buffer size minus 1 items to be used. That means one space is wasted. Not much of a caveat, but yeah, I mean that is there. The one space is wasted. Now this is some sample code what the producer and consumer can do. Okay. So the font is a bit small. I hope you can see it. So basically, what does the producer do? So it's running in a loop, produce an item, check whether the buffer is full. If yes, so while the buffer is full, wait. Right, there is no free buffer, so do nothing. And once the producer comes out of this loop, it just produces the new item and adds it in buffer in, and then it increases in by 1. Not only increases by 1, but modulo buffer size, and that is how we make this buffer behave logically like a circular buffer. Right, I hope this is clear. What does the consumer do? Again, it checks if the buffer is empty while in equal to out. And as long as the buffer is empty, it has to wait. If the buffer is not empty, then remove an item from the buffer and increase out. So out equals to out plus 1 modulo buffer size. Right. So this is how the producer can behave and consumer can behave. So as you understand, this buffer, in, out, these are in the shared memory. So the producer and the consumer both should have access to these variables, these data structures, buffer, in, out. So any questions here? In the first while, if it is in, so what are you asking? In the first while, if it is, so what is the question? Can you unmute yourself, Shaumitro?
Yes, sir.
Yeah, what is the question?
Sir, if it was in percentage modulo buffer size equal to out, then the one memory was yes, sir.
Okay.
Sir, every time we are incrementing inside the while loop in equal to in plus 1 percentage buffer size. So if it is no need, if we don't do this, so, then the one memory loss will not be there.
Sure, agreed. I mean, this is just one way. There are different other ways. We will in fact discuss another way where the memory loss won't be there. But okay, maybe what you are telling is correct, but again, so I'm not focusing too much on how to avoid that one memory loss. I'm just giving this an example of how to use shared memory. Sure, there are better mechanisms of avoiding that one memory, I mean, wastage of one memory item. Okay. So what you are saying probably is correct, but I have not checked. But sure, I mean, feel free to try it out. Any other questions? Okay, if not, yes. So this is the correct solution, but with that one small caveat that one item is wasted. So what can be a better way? One which Shaumitro was suggesting. I have not checked that, but it's quite possible that it is correct. let's discuss any other idea as to how this, maybe a simpler idea of how this one memory wastage can be minimized or can be eradicated. Like, can you think a slight out of the box, as in, can you do something other than using this in and out? Can that simplify things, yet avoid that one memory item loss? I mean, if I tell you the solution, you will see it's so simple. But yeah, systems are often built on these simple ideas. Linked list. Okay, sure, but then, as you know, a lot of overheads would be there, etc., etc. So Rahul, we are doing practically something similar, like, right, in and out, you can think of back and front, etc. Okay, in the interest of time, let me tell you, it's a very simple solution. Maybe all of you are thinking of more complicated solutions, and maybe there are, I mean, surely there are multiple solutions which many of you may be thinking. A simple solution is this: just maintain an integer count as to the number of filled buffers. This count is the number of filled buffers. Initially, count is set to 0. The producer increments this count after it produces a new item, and it's decremented by consumer after it consumes a new item. As simple as that. So when count is equal to 0, the buffer is empty. When count equal to the buffer size, the buffer is full. As simple as that. This is now the code. So again, count, buffer, these are shared memories, right? And in and out has to be maintained, because other than that, the producer don't know where to put the next item, and the consumer don't know from where to read the next item. In and out has to be maintained. But now if you see, we are not using in and out to understand if the buffer is full or not. Rather, we are just checking this or this. So as simple as that. Okay. But of course, there can be other solutions which will also avoid this one memory place loss. This is just one of them. I hope you agree that this is a simple solution. So again, systems are often improved based on simple ideas. Okay, that was our discussion on shared memories. Any questions? Otherwise, we will pass on to the next IPC mechanism, which is message passing. Okay, let me move on. So again, message passing is another IPC mechanism for processors to communicate and synchronize their actions. So this mechanism does not use any shared variable in the memory, but it uses something called pipes. And IPC provide, so two system calls are given. First of all, you have to create the pipe, for which there will be a set of other calls. We'll come to that. But in general, you send using this send call, send a message, and receive a message using the receive call. As simple as that. Okay. Message size is either fixed or variable. Now, this is the communication model. There are these two processors, and there is a particular area, sometimes in the memory, sometimes maybe even in the disk, etc., where this message queue is maintained. So process A can send messages to this, and B can read from it. Process A can send messages, and B can read from it. Okay. There are two ways of such message passing: pipes, sometimes called ordinary pipes, and named pipes. Okay. Let's discuss these two. So, in general, pipes act as a medium to allow two processors to communicate. I think from the second DAB assignment that you have done, you have got a fair idea of pipes. and therefore I expect this part to be kind of known, so I am moving quickly. Of course, if you have any questions, then ask. But in the second assignment you implemented pipes, right? Because that shell asked you to have, when the shell building assignment made you write codes like when output of one command is going to another command using through pipes. Right? You understand, you have done that, right? Yeah. So this part actually is known. So I'm just going through. Yeah, so there are some interesting questions to be answered, like with pipes. Can any two processes communicate via pipes? Or should there be an relationship between the two processes? Example, parent-child, for using a pipe. Or another question is, can the pipes be used over a network? So the answer to this question for us is no. For this, I mean, send and receive can be used, but that uses, I mean, if you want to work over a network, then that would require some other mechanisms like sockets and all, which again you will study in the networks course. But yeah, this is an interesting question. Must there exist a relationship between the communicating processes? Can it be that only a parent and child can communicate via pipes? Or can it be that any two processes can communicate via pipes, even if they are not parent-child, etc.? So let's see the answers. Okay, Srihash has said any two processes can communicate via pipe. It's true, like it's partially true. That is possibly what you have seen also. But yeah, there are actually, I mean, both, and that is why there are two types of pipes: unnamed pipes and named pipes. Yeah, you are right. So Akshat, Srihash, Pankaj, I agree. What you have done in your assignment is allows both, I mean, any two processes to communicate. But let's see the complete answer. So as I said, there are two types of pipes: ordinary pipes and named pipes. So ordinary pipes is the message passing medium between related processes. So this cannot be accessed from outside these related processes. So typically a parent process creates a pipe and uses it to communicate with its child process. Okay. So this is a mechanism for the child and the parent to communicate. And usually this is unidirectional communication. That means the parent wants to direct the child in doing some particular tasks. Right? So typically a parent process creates a pipe and then forks a child so that the child also gets the access to that pipe and then uses it to send some messages to the child. So pipes behave like FIFO queues, and it is very similar to what we discussed in the producer-consumer problem. So the producer writes to one end of the pipe, which is the right end, and the consumer reads from the other end, which is the read end of the pipe, right? This is very similar to, again, I mean, using pipes also you can implement the producer-consumer paradigm that we discussed. So again, the producer-consumer paradigm is just a abstract paradigm. There can be many different implementations of it. I think you are all very familiar with the term abstract data type. Similarly, producer-consumer problem is kind of an abstract notion. There can be many implementations of that notion. We discussed one using shared memories. Pipes can also be used. Okay. So yeah, but these ordinary pipes, these are mainly for communication between a parent and a child, and they cannot be used outside these processes. So this is an ordinary pipe. Of course, this is not the only type of pipes. Okay. So this is the producer-consumer using pipes. I mean, as simple as that. So while true, the producer says while true, it just sends the next produced item, and consumer just checks, like, just receive the next consumed item. Right. So in these pipes are, you are taking the kernel support to create these pipes. So if there is a situation where pipes can become full, etc., that the kernel will handle. That's why the producer consumer do not need to check if the pipe is full or the pipe is empty and so on. That part the kernel is handling. So the producer consumer can simply write to the pipe at one end, which is the write end, and the consumer can read from the other end of the pipe, which is the read end. Okay. Yeah. Okay. So this was ordinary pipes. But there is a better version, which you have used in the assignment, which is called named pipes. So this named pipe is actually accessed like a file by processes. And the advantage is that no parent-child relation is necessary. So any two processes can communicate using a named pipe. So they also behave, similar to ordinary pipes, they also behave like FIFO queues. Sometimes these are also called FIFO. And several processes can use the named pipe together. Right. So this is how things work. So I think again you are kind of familiar with this code because you have done the second assignment. So here there's a char pointer, like a temporary file, let's say, and you create this FIFO pipe using this make FIFO, right? So the make FIFO will create a pipe, and again you have to give permissions, etc. And then say this process A, this is the producer. So this opens the pipe in WR only mode. Okay, WR only mode, so write only. So A only wants to write to it. Then it can write and then close the pipe. And the process B is a consumer, so that opens the same pipe using this mode, O read only. So this wants to read from the pipe. So it can read from the pipe, and then when it is done, it can close. Yeah. So this is how a named pipe works, right? Okay, Pankaj has an interesting question. If named pipes exist, what is the need of existence of a normal pipe? Ordinary pipe. Parents and child can also use them instead. I agree, possibly they can. I'm not very sure, but one thing that I can think of is, say, things like privacy or security. Say, if actually a parent and the child want to communicate, they might want to use a secure medium which no other process can access. So remember, this named pipe, any other process can also start using this pipe, possibly. But an ordinary pipe is within a parent and the child, so it's less likely to be snooped in by other processes and so on. Right, so that is one possible reason which I can think of. So remember, there are many other aspects which we are not discussing in this course, aspects like security and so on. So this is one reason which I can think of. Okay. Yeah, so possibly throughout this course, we won't discuss much about security mechanisms and things like that. We are assuming that all processes are nice processes. They are cooperating. All of them are following the rules of the kernel. Sometimes some processes may not like to do that, and we know from real life that there can be such things. So a large part of the operating system design or kernel design has to take care of security issues. So that this can be one of those reasons why there is still a ordinary pipe. Okay. So yeah, so just the thing is, in case of this FIFO or named pipes, so once you have created a FIFO special file or a named pipe, then any process can open it for reading or writing in the same way as an ordinary file. However, with one restriction, that it has to be open at both ends simultaneously before you can proceed to do any input or output operations on it. Just one quick question, like bit of a distraction still. Do these two lines seem familiar? Have any of you read these two lines earlier? The two lines in this slide, do they seem familiar? Okay, no, wait. I'm asking a much more specific question. Not the concepts. Exactly these two lines, the language, the words, do they seem familiar? Like somewhere I have read this line. If not, that is a bit of a worry. Okay, so let me just say, yeah, these two lines are taken from the man page of pipe, right? So these two lines are taken from the man page of pipe. So if you have not yet developed the habit of going through man pages, I would seriously suggest you do. Right, man pages are possibly the most authoritative sources of information about system calls and commands. Right, so if you have not yet developed the habit of going through man pages, please do so. Man pages may not be always easy to understand. There are lots of details. Maybe you will need only 5% of the details that are there in the man pages. But even then, it's good to have the habit of reading man pages. Even we don't understand all man pages. That's okay. Some man pages are really complex. Some parts of man pages are really complex. But even if you don't understand all the parts, it's good to go through man pages because they are the most authoritative sources of documentation about these system calls and commands. So do start going through man pages. Okay. So yeah, so that was our discussion on named pipes. We don't need a, I believe we don't need a more detailed discussion because we have already done assignment 2. And this is one thing which we are not discussing, as I said, that for communication of two processes over a network, we have to use things like sockets and remote procedure call, which I guess would be covered in your network course. Okay. Fine. So this is a summary slide, which is just to summarize what we have discussed till now about processes. So we discussed about the structure of a process in memory and the different states in which a process can be. And we discussed the state transition diagram, etc. Then we discussed the process control block, which is the representation of a process in the kernel. So the kernel has to do various bookkeeping activities about processes. For example, it has to know in which state a process is, and the kernel has to change the state of a process, etc. Therefore, it must be using some kind of data structures. And yes, the process control block is used to, so by the kernel to maintain records about a process. So every process has a PCB. And then we briefly discussed what happens during a context switch. So the kernel has, so suppose process A was running, the kernel came, the process A was running on the processor, kernel was allocated the processor. How? Possibly by some timer interrupt, or A itself made a system call by which kernel got the control, right? There are typically these two mechanisms. Either A makes a system call, like an IO operation or one of these system calls, fork, etc. Then the kernel gets the, so the control goes to the kernel. The kernel now has the processor to itself. Or it may happen that A did not make any system call or request any IO operation, etc. But the timer interrupted, right? Then also the control will go to the kernel and the kernel will get the processor. So now the kernel can execute. First thing it should do is it should save the state of A, process A, which was executing, unless of course A is terminated. So it has to save the state of A because at some point A should be resumed. Then possibly a scheduler will run and it will decide which other process to execute next. There are many other things. Now we are actually seeing many other things which need to be done. For example, the states of different processes may need to be changed. Right. So maybe some other process X was in the waiting queue of a device because it had earlier requested for I/O, but now that I/O has been completed. So maybe the state of that X has to be changed. So there can be many other bookkeeping activities which the kernel needs to do. Finally, one of these activities is that it has to decide which is the next process which should run. So there is a part of the kernel, a procedure which is called scheduler. The scheduler will look at all processes in the ready queue and decide which process to run next. Then there is another part called dispatcher, which will load this selected process to the kernel, to the processor. So the dispatcher will actually allocate the processor to this process which is selected by the scheduler. And then the control will be shifted to this process B. That means the CPU will be allocated to B. So this will happen during a context switch. And we typically want this to be quick because context switches will happen many times in every second. Then we discussed queues for process scheduling. There are different queues like ready queue, event queue, and we discussed a queuing diagram. So a process state transition diagram we also discussed, and a queuing diagram we discussed. Both of these can be used to understand how a process changes from one state to another, or how a process or a PCB of the process is moved from one queue to another during the lifetime of a process. And finally, we discussed how processes talk or communicate, and we discussed shared memory, pipes, and end pipes. Something which is not written and we discussed. We also discussed creation of a process, one process waiting for another, and so on. Right. So that is also we have discussed. So, but okay. So now, final question for today from me. There is one part here which is kind of incompletely discussed. Which is that part? Something which we have not discussed yet. We have said we will discuss. Something to do with scheduling possibly. Yeah, context switch. So we have discussed what happens during a context switch, but there is one part which we have not discussed. Which is that part? Bit more specific answer? Yes, we have not discussed the scheduling algorithm. So as part of a context switch, one step is that the scheduler will look at all processes in the ready queue and decide which process will start next. How will it decide? What algorithm will it use to choose which process should execute next? Those exact algorithms we have not discussed. So that is what we will do starting in the next class. Okay, so that's all for today. Any questions? Okay, if not, then fine. Then let's end this class today, and we will continue again next week. By the way, just one announcement, quick announcement before I forget. So we will send out an assignment in this OS theory for you to complete. We will send it out today or tomorrow. It will be based on whatever we have discussed till now. It's a simple assignment, and we will tell you exactly how you have to submit, etc. Okay. So we will send out an assignment of OS theory in the next couple of days. Okay, then let's end this class. Thank you, everyone.